Good morning, students. Today we're going to be doing exponential growth and decay. The nice thing about this section is that it is all review. You've done it back in Algebra II, and you did it in pre-calculus trig. So let's start off with the equation that we're going to be using throughout this section, and it is this. Y is equal to c times e to the kt. Let me tell you what each of these variables stand for. Your c here is your initial quantity. T will be time. That's going to be in seconds, minutes, years. It'll be given in the problem. K here is the constant of growth or decay. Constant of growth or decay. And I'm going to put a star here because really working these problems really hinges on finding K first. Y then is going to be the quantity. That's not two T's, that's one. After T time periods. Again, that's going to be problem specific. So let's go ahead and work through a problem that you may have seen before in the past, and that is a half-life problem. All right, the half-life of radium-226 is 1,620 years. Find the time required for a 5-gram sample to decay to 1.3 grams. All right, now as I said before, what we want to do is we want to find K first. Oddly enough, or interestingly enough, half-life problems happen to be two-step problems. And what we're going to do is find K first. Now look, for half-life, it doesn't matter if you start with 6 tons of radium-226 or 6 pounds or 6 ounces. The time required for half of that original sample to decay to half of the original quantity is 1,620 years. It's the same regardless of what you start with. I think that's obvious, which means we're going to pick easy numbers. Like, for instance, you could start with 2 grams, leaving you 1 gram after 1,620 years. All we need to do now is solve for K. So I'm first going to divide by 2 on both sides. That leaves me a half. Incidentally, you could have started with 1 and decayed to a half. Obviously, it's 1/2 e to the 1620k. I bring the e to the other side. I'm going to natural log a half. That's 1620k. I divide by 1620. So k turns out to be the natural log of 1/2 divided by 1,620. Incidentally, when you plug this into your graphing calculator, you want to make sure that you enclose the half into parentheses. Otherwise, you're going to be natural logging the entire numeric portion of that fraction, and that's not something that you want. You only want to natural log the half. And so when you punch this into your calculator, you get something like negative 4.27 blah, 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 times 10 to the negative 4th power. Now, it's very important that you do not round K. For exponential growth and decay problems, because the time periods are so long, you end up, and the growth is so drastic that you end up with wildly incorrect answers if you start rounding the inputs. So what we want to do is we want to store K into your graphing calculator. And the way we're going to do that is we're going to hit the store button. That's STO with a little caret to the side. And then I want to hit alpha, which is a green button on most of your calculators in the upper left near the math button. And then I want to hit store alpha and then K. And K is the left-hand parenthesis with the small green K above it. So we're going to store this number into K in our calculator. Now, you don't need to worry about erasing this when you move to another problem. Every time you store a K into K, it overwrites the previous value. So that's all taken care of. So again, it is store alpha, left-hand parenthesis, and then of course we need to enter it. All right, so let's go ahead and work this problem. Once you've got K now, I can actually go about solving this problem, so let's do that. All right, so what I've got is a half-life of 1620. I want to know the time required, so I'm solving for T, and I want 5 grams to decay to 1.3 grams in a certain amount of time, and I'm trying to find that t value. All right, so here we go. I divide by 1.3 by 5, both sides by 5. I'm going to then natural log that quantity. And then, of course, k is the numeric value that I have stored in my calculator, so I'm going to divide both sides by k. That cancels on the right-hand side, and t should be 3,148.335. And that, of course, is going to be in years. All right. Let's move on to some financial planning. If you recall, back in the day in Algebra II, you had Apple Runt or Apple Run, and then you had a PERT. Let me tell you what these stand for, and I'll show you how these two equations relate. Now, this has to do with calculating compound interest, the effect, rather, of compound interest on a deposit in an interest-bearing account. All right, so for both of these, P turns out to be the principal. This is the original amount. Let's see here. A, in both cases, is the amount in the account after t years. R is equal to the interest rate. I should say this is going to be in decimal form. T, of course, is time in years because we're dealing with annual interest rates. And N, even though we're not really going to be using the Apple Runt, N is the number of compoundings per year. Now, the way compound interest works is they will calculate interest on the amount that you have in the bank, and they put that interest accrued over that short time period into the account. So your principal grows. The original amount continues to grow as the number of compoundings increases. As I said before, in this section of the book, we're going to be primarily concerned with a PERT, and I will show you at the end of this video how to get from Apple Runt to a PERT and why a PERT is the way that it is. Now, I should talk about a PERT because a PERT is used to calculate interest when it is continuously compounded, which essentially means an infinite number of annual compoundings. And that will be stated actually in compounded continuously will be stated in the problem. So let's go ahead and work a problem. We'll show you how this works. It's very similar. In fact, it's exactly the same as exponential growth. Might look something like this. Find the time it takes for a $15,000 investment to double at a 5% interest rate compounded continuously. All right. So we'll make our principal $15,000. If it's going to double, it's going to grow to 30,000. I've got E to the 0.05 times T. Just keep in mind, 5% needs to be in decimal form, otherwise your answer is going to be wildly incorrect. All right, just like we did before, I'm going to take 30,000 rather, divide it by 30. That's going to be not 3, Mr. Carver, that would be 2. By the way, you could still start with 1, make C 1 and make your Y 2. Because again, at 5% interest compounded continuously, the amount of time it takes to double is the same regardless of what you start with. I now have that times E, equal rather, to E to the 0.05t. I'm going to bring the E over. I will natural log 2. I've got 0.05t, and then I want to divide by 0.05. So it's the natural log of 2, enter, divide by 0.05, and t turns out 13.863 years. By the way, in business school, they do teach you the rule of 72. The rule of 72 is if you take 72 divided by the interest rate, it gives you an approximate length of time it takes for an initial investment rather to double in time. And if you take 72 divided by 5, you do get 14.4. So it's a rough estimate, but and by the way, that comes from the natural log of 2, but that's a topic for another day. All right, so I'm going to show you how then to go from apple runt then to a pert. I think that's pretty much everything you're going to need to know to get through tonight's homework. If you want to stick around and watch this, you can. I'm not going to ask you for it. If you're interested in seeing it, then you can certainly keep watching. All right, so before I start this process, I should mention this. This is important to know. If I take the limit as n goes to infinity of 1 plus 1 over n to the n, I actually get e. And you can try this on your calculator. E, by the way, is 2.71828. That's an irrational number, goes on forever and ever. The larger n is, the closer you get to this exact value, or, well, the exact value of the rational number, which again continues indefinitely without end or pattern. If I then take this, the limit as n goes to infinity of 1 plus 2 over n to the n, that gives me e squared. And then it would make sense that if I take the limit as n goes to infinity of 1 plus r over n to the n, I get e to the r. Now, if I take apple runt, you can already see where this is going. If I take this portion just right here, and remember, n, if I use apple runt, that is a limited or finite number of compoundings. A pert is an infinite number of compoundings, so I think it would make sense that as n goes to infinity of 1 plus r over n, just as I said above, that gives me e to the r. So if I replace this bracketed portion with e to the r, I get p times e to the r to the t. Power to a power, you multiply. This is pert, which gives me a pert, which is y. I switch from apple runt to a pert as the number of compoundings grows to infinity. All right, guys, thanks for tuning in, and we'll see you soon.